G'day YouTube, Warbles on a lot here, ready to discuss the relative efficiency of foam chuck gliders versus folded paper aeroplanes. In the previous video, flight tests were conducted. Look for it in my scroll. We discussed how the Papuan Highland dart, this being the original design, launches at high speed, and then when it slows down, it opens up, increasing its wing surface area by at least 35%. So it's a aerodynamically controlled variable geometry, variable area model aeroplane. Cost 1,000 sheets for $5, half a cent each, 200 for the dollar. Slightly different folding may be used to increase the wing area and decrease the side area, resulting in the modified Papuan Highland dart, a process which may be continued from the sublime, literally, to the ridiculous. Stacking them the other way up demonstrates the process by which the aircraft can be made to have a progressively larger wing, which gives it more lift, more drag, and therefore it flies slower. Hopefully this will work. The highest modified raised its nose, stalled out, landed early. Standard model was on the ground fairly quickly with a small wing, and the modified stayed in the air for the longest time. Standard model, modified, extremely modified. Okay. 1, 2, 3, 4, 5, 6 paces. One, 2, 3, 4, 5, 6, 7, 8, 9, 10 paces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 paces. The 3 Papuan Highland darts, 3 versions of it, were flown off against the traditional European water bomb, which has a conventional KF wing, whereas this has an inverted KF wing. And whereas the dart is beautifully streamlined, the water bomb's got all this crap and crud hanging out at the front of it, and it needs elevators torn into the trailing edge for it to fly, and it does fly, but it's slow. One, 2, 3, 4, 5 paces. Okay, so the Papuan Highland dart beats the hell out of the European water bomb. Technically, the more you modify the dart, the better it flies. But when it's extremely modified, it becomes extremely twitchy and extremely slow, but not as slow as a water bomb. Okay, so these were flown off, the modified dart versus the Firefox. A moulded 3-piece styrofoam glider, which comes in a plastic bag with a set of paints. Costs $5, but the paints are dried out, so it'll cost you another $5 if you were to paint it. This one, which has been pre-manufactured with an internal weight, and which also has two little dimples to show you where to put your finger and thumb when launching. See the dimple? It's a lot heavier than the paper planes, with a much smaller wing, therefore it has to fly faster. And it goes further until it gets shot out of the air by a tea tree. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It got as far as the best paper aeroplane, and then it got shot down, and it would probably have gone maybe another 6 paces further. So as you can see, we're sort of comparing chalk and cheese. $5 for an unpainted foam glider, half a cent for an unpainted paper aeroplane. And the paper aeroplane stays up for longer because it's lighter and it flies slower. To square this circle, let's take the observed flight times of the modified Papuan Highland dart, which I learnt to make in 1973 at De La Salle College, Armidale, taught to me by a Papuan Highlander who apparently learnt it when he was a kid in the jungle village, versus the foam Firefox. Right, let's go look at some numbers and see what we can see. During the earlier video to which I alluded, I spent a fair bit of time walking up and down the hill chasing a paper aeroplane, a bunch of them actually, and a foam glider. And I paced out their flight paths and I made due allowance for the wind on the day. What we get is a paper aeroplane that weighs 4.2 grams. Its average flight duration was 20 seconds. Its average distance was 65 metres. The height loss was 5 metres. The airspeed was 8.662 miles per hour or 13.93 kilometres per hour. Sink rate was 0.8 feet per second or 48 feet a minute, which is 0.25 of a metre per second, giving a glide ratio of 15.875 to 1, which is not bad for a half cent worth of paper aeroplane. Up against the foam glider, 14.9 grams, 9 seconds duration, 38.5 metres flight, 2.75 metres of height loss, 11.025 miles per hour, which is 17.74 kilometres per hour, 0.902 feet per second sink rate, which is 54 feet a minute, or 0.275 metres per second, which gives a glide ratio of 17.849 to 1. Okay, so how do you decide what that means and which is actually your best, most efficient model aeroplane? Well, you could work it out on what's lighter and what's slower and what's got a better sink rate and what's got a worse lift drag and what's got a better duration. Another option would be to graph the results, perhaps using weight as a constant with sink rate, airspeed and glide ratio as variables. Or we could use sink rate as the constant with weight and airspeed and glide ratio as variables. We could plot airspeed against weight and sink rate and glide ratio. Not to forget glide ratio versus sink rate, airspeed and weight. And because it's my video, I get to decide the order in which the plots will be drawn. So we'll start with weight, then we'll do sink rate, then we'll do glide ratio, then we'll do airspeed. The dart has a weight of 4.2 grams. It flies at 8.6 miles per hour. It has a sink rate of 0.8 feet per second. and a glide angle of 15.875 to 1. Plot the intersection of airspeed and weight, connect the sink rate to the previously mentioned intersection, then connect the speed-weight intersection to the glide ratio. And there you have the dart, plotted according to weight being the constant, versus 14.9 grams of Firefox. Extend that up, and then across to the 11.025 miles per hour. Then we have the 0.902 feet per second sink rate. And the glide angle is 17.849 to 1. And that gives us a graph. Doesn't actually help to visualize anything, so let's try plotting a different set of axes. Okay, let's have a go at the same numbers with sink rate being the constant. And the dart graphs like that, and the Firefox, it charts across there, above and to the right, on both of those graphs. So now we'll make glide ratio the constant. See if anything more interesting shows up. Showing us the dart. Okay, and after a couple of graphs that look fairly similar, we now have one that's different. It deviates. Basically, it reflects the enormous weight of the foam chuck glider compared to that of the paper aeroplane. 4.2 versus 14.9 grams. It has to fly fast because it has to make a lot of lift because it has to carry all that weight. So these graphs are starting to make sense, but they don't actually illustrate anything particularly well, in my opinion. One more time, onto the pen and rulers. Let's see what we get when we consider airspeed to be the constant. And this gives the Papuan Highland dart a similar style of a curve to that displayed by the Firefox on the previous graph, where glide ratio rather than airspeed was the constant on the bottom. And yeah, I've continued that vertical line up from the airspeed for a reason. Okay, so now we have the Firefox on top in blue, and we have the Papuan Highland Delta Dart below it in green. Still doesn't actually tell us much about the difference between the two aeroplanes and why it is so. Therefore, I came up with a new wrinkle. If we project the glide ratio across to the airspeed line on both these graphs, which is, I confess, why I extended both of them vertically upwards, we find the dart graph enclosing a narrow, pointy little triangle. Whereas, conducting the same exercise with the Firefox, and what this graph shows is that the Firefox is 21.5% faster and has airspeed doubles, drag squares. Whereas the paper plane has 44% of the surface area, because I'm figuring that this blunt edge on the triangle, that's analogous to the frontal area of the two aircraft. This is quite a fat little porker compared to this. And it's a heavy, fat little porker. And the fat, heavy little porker does not have the advantage of variable geometry, airspeed controlled. Okay, so 2/3 lighter, 66%. 21.5% slower, 11.5% better sink rate, 11% worse lift drag, 55% better duration. So you could say that it's 100% better. 354% heavier, 21.5% faster, 11.5% worse sink rate, 11% better lift drag, 55% worse duration. So, yeah, 388% less efficient in terms of how heavy it is and how long it flies for. Seems a bit harsh to me, but that is a raw analysis of the numbers. Graphically, slightly different picture. In terms of weight, 65% lighter. That's got to be good. 11.5% lower sink rate, so it stays in the air longer because it's lighter. So that makes it 76.5% better from that point of view. Come over here and you got 21.5% slower. Now, a lot of people are going to say faster is better, so we'll accept that. Going slower, yeah, it can be regarded as a disadvantage. And then we have 11% worse glide ratio on the part of the Dart. So what you've got is, in two factors, the Firefox is 32.5% better than the Dart. And in two different factors, the Dart is 76.5% better than the Firefox, which means that overall, your half-cent paper aeroplane is 44% more efficient aerodynamically. It stays up for longer, it flies slower, it's lighter, it has less frontal area. And I think they're facts worth knowing. In a later video entirely, I will address the issue that it's a lot easier to paint and decorate your $5 foam chuck glider, which actually they come with paints and destructions in the bag. But like I said, that's another story. If we forget about the paint job, at this point, just concentrate on the fact that the paper aeroplane, which costs half a cent, outperforms the foam chuck glider by 44%. All things considered, 44% more efficient at 1,000th of the price. Who says I'm a mad scientist? And why do they want to know? Warbles on a lot to YouTube. Ciao.